So when Natalie came to Sonoma State, she wasn't initially a physics major. And I met her in the 114 physics class where she was taking it sort of out of curiosity. In that class, after the first 2 tests, I noticed that she got an A on each of her tests. So I approached her to see if she might be interested in pursuing physics as a major. However, she wasn't sure. She wasn't sure if she could become a physics major or see it through to completion. So I said, well, let's see how test 3 goes, and then we can make a decision. And sorry to the other students who were in that class, but I actually made test 3 a little harder, just to see if she really would get an A in that class. And sure enough, she got an A. So I was at least convinced that she could do physics. Since then, the UC Irvine Graduate Admission Committee is also convinced that she can do physics, but can Natalie do physics? I leave it to our audience to decide.
All right, well, hi everyone. My name is Natalie Sanborn. The research I've been working on this semester is simulating data for the James Webb Space Telescope, abbreviated here as JWST, and I have been working with Dr. Thomas Targett. So in order to first start talking about the James Webb Telescope, I'm going to talk about the Hubble Space Telescope. So the Hubble Space Telescope has been orbiting around the Earth since 1990, so it's been there for a while. And in that time, it has taken a lot of amazing observations. It has done observations close to us in our own solar system and all the way to 13.4 billion light years away, which is really far, and everything in between. So here I have a picture of the Hubble telescope, and Hubble produced this Hubble Ultra Deep Field image. And if you haven't seen this image before today, you at least saw it in Zoe's presentation. It's a very famous image produced by Hubble. So the reason I started off by talking about the Hubble telescope is because the James Webb telescope is effectively a successor to the Hubble telescope. It has improvements compared to Hubble. It's brand new. It just launched at the end of last year, and it's going to start collecting and sending data this summer. So it's a very current topic. And here I have a picture of the James Webb telescope. It has, that yellow part is the mirror. And we're hoping that it's going to be able to take a lot of observations that are even better than Hubble. So you saw that picture that Hubble took. We're hoping for better ones from James Webb. And Professor Targett told me that he would not let me graduate if I did not include this slide. So I mentioned that there are a lot of improvements in the James Webb telescope that are better than what we had with Hubble. One of these is the mirror size. So the mirror on the James Webb telescope is 6.5 meters in diameter. This is in comparison to the 2.4 meter diameter mirror in the Hubble telescope. And one of the reasons that a larger mirror is better is because there's more light collection and a better angular resolution. This angular resolution means that the images that it takes will be clearer. Another reason that is an improvement in the James Webb telescope over Hubble is the location of it. So James Webb will be at the Lagrange 2 point. And what this point is a stable point in space that is, see if I can use this, right here. So if this is the sun and this is the Earth, here is the Lagrange 2 point. It's a stable point, stable because of the forces of gravity from the Earth and the sun. And it is also significantly further away from the Earth than Hubble was. So as you can see from this image here, the James Webb telescope is 1.5 million kilometers from the Earth, compared to Hubble, which is in orbit and is only 570 kilometers from the Earth. And for reference, we also have the moon. So going back to this Lagrange 2 point, it actually orbits with the Earth around the sun. So you can see that point number 2, and it's going around and it's following the orbit of the Earth. This is really important because since it's there, it will kind of always be in the same spot relative to the Earth, which is important so that the communications and signals, it's not hard to find. It's not like the orbit's out of sync and it's always going to be in a different place. And also, since it's so much further away from the Earth than Hubble was, there will be less heat interference, which is important because the James Webb Telescope uses infrared observation. And since it's further from the Earth and also shielded from the sun by the Earth, there will be less heat. So going back to talking about Hubble, in my previous slide, I had the Hubble telescope created this image, the ultra deep field image. And from this image, scientists were able to create a luminosity function, which describes the universe based on the x-axis here is the absolute magnitude of objects, and the y-axis has the number of objects with that absolute magnitude. So this, from the Hubble observations, they created a luminosity function for specifically redshifts of z7 to 8. Redshift corresponds to distance. So these are the distances that Hubble was observing, is that 7 to 8 range. So from the data in the image, we created the luminosity function. And then for James Webb, this luminosity function that describes redshift 7 to 8 was extrapolated. It was extended, assuming that a lot of the patterns will follow for a higher redshift of Z9 to 10. And this Z9 to 10 is important because that is what James Webb will be doing its observations in. So this creates a model of what we would expect to see at these higher redshifts that James Webb will be observing. So from this luminosity function, 9 to 10, scientists created a mock catalog of data. And this mock catalog is fake galaxies and light sources that match that luminosity function for the range of 9 to 10. And the reason that this was done is because we don't have the data from James Webb yet, so we're starting off with simulations. By using this mock data, we're able to prepare for data analysis of the James Webb observations with the mock data. And so that's what's here, is this is a simulated image created with that mock data. The mock data is known as the JADES catalog of data, and it models what we would expect to see with the James Webb telescope. And this image uses the data in the catalog, but it has noise on top of it, because in real life, in real observations, there will be noise. There's not noise in the catalog, that's just pure data sources. And with the noise, we can model what we might be able to see through the telescope. So what I've been working with is using the simulated data and determining the limiting magnitude in the simulated data. So the first step in this is, what is the limiting magnitude? A limiting magnitude describes where it's the limit of the brightness of objects that a telescope or even the human eye could see. So I have here a chart. It has flux on the x-axis and number of objects with that flux on the y-axis. This chart is from the mock catalog of data. And a higher flux value corresponds to a brighter object. So, for example, this line here might represent where a ground telescope could see. So it would be able to see everything brighter in this range, 8 to 12. It would be able to see all of that, but everything behind here, all of these lower flux values, would be obscured by noise. And then this green line might represent what Hubble could see. So it can see even further, it can see fainter objects, but there's still everything over here that Hubble's not able to see. And then the James Webb telescope is able to see even further than Hubble, but obviously there's still all of this over here that's obscured by noise, just because the limits of technology. And the lower flux values correspond with a higher magnitude value. They're inversely proportional. So that's important when I describe what the actual limiting magnitude we found was. So what I've been doing is using the simulated images. I had that orange square image on a previous slide, and determining what the limiting magnitude in the image is, because those images were created with a specific limiting magnitude in mind, And we want to be able to confirm that it matches with what was actually in the image to prepare for actual data analysis. So the first step with this was plotting the mock catalog of data. And this is, like I said, the raw data. There's no noise on top of it. So that'll show us really what's in the catalog. So here I have, once again, the flux on the x-axis and the number of objects with that flux on the y-axis. And you can see in blue, this is the data straight from the catalog. And then when images are created with that data, and I analyzed the images to determine what we could see in the image, you get this orange graph. And you can see there's a little bit less in the simulated image than there is in the actual data catalog that went into the image. And this is what we expected to see because there's noise and other factors that make not every single source in the catalog is going to be able to stand out in the image. So I made quite a few plots like this because this was tested over a variety of wavelengths in infrared wavelengths, near infrared, and optical wavelengths to determine that they're all consistent. And you can see that there is the drop-off point on the simulation right here, and that drop-off point is how we would determine the limiting magnitude. So I have, like I said, other wavelengths, and this is a very similar thing, but a different wavelength. I have them side by side so you can see what they look like separately. Here's another one with them on top of each other. And it turns out that the limiting magnitude is greater than 29 in the AB magnitude system, which is consistent with what went into the simulated images, and confirms that it was created properly to help prepare for how we would analyze actual data from James Webb. Thank you.
Any questions?
So you talk about how there's so much noise, especially at these, like just looking, there's so much noise deep beyond. How do we get these isolated photos of galaxies or like star systems, and you pretty much just see black in the background? There's no noise. How do we get those?
I don't know the answer to that. I feel like that's probably something I have learned the answer to in an astronomy class I've taken. But it probably depends on like the significance of like standard deviation that the objects are actually standing out compared to the rest of the noise. And that's something like when I was using the image, like, I don't know where it went. But the orange square image, and you could see that there were like some sources that stood out more than others. I just used a program that told me which of those were like real sources. So there's some kind of math that goes into that to probably determine like what is significant to be considered like an actual galaxy or star.
What are sources of noise for the James Webb Space Telescope?
I don't know, just other light and wavelengths in the, like I said, there would be less heat interference since it's going to be further from the Earth, but there's still going to be some interference. And I imagine that would be creating some of the noise.
Do you think you're going to want to continue on this work in graduate school or try something new? Or?
I don't know. I had some time to figure that out. I think I'm probably going to try a couple things to see what really sticks. But so far, kind of cosmology has kind of been what I've been doing. So, yeah.
All right, any final questions for Natalie? If not, let's thank her again.